So the first thing we're going to do here is we're going to review, or we're going to look at how we will prove an algebraic equation. What you have to do is you're looking at an algebraic equation and you want one side of the equation to equal the other side. So what I'm going to do, and you always inevitably want to pick the harder side to start simplifying, because on this equation, I know it's hard to see, but I'll rewrite it. On this equation, you can't really simplify 2 down anymore. So we're instead going to work on this more complex side, simplify it down so that we can eventually end up with the answer of 2. So it's like a puzzle. We're trying to figure out how x on this left-hand side equals 2. That's what we're doing right now. Now, here, I wrote it way too big. First thing I'm going to do, well, let me ask you, what do you think the first thing I would do here is? What can I do here? Yes, I would get a common denominator because notice that 2 is just a single term. On the left side, I have currently 2 terms being subtracted. So a good solid move to make is trying to combine those into a single term. And yes, to get a common denominator, you would multiply by the opposite denominator. So I'm going to multiply this side by x plus 1 over x plus 1, and multiply this side by the other denominator of x minus 1 over x minus 1. Now for now, I'm going to keep the numerator separate. So I'm not actually going to distribute um, these 2 binomials together. I'm just going to for now leave it as x plus 1 times x squared minus 1 minus x squared minus 1 times x minus 1. And I will, however, multiply my denominators. Now, the reason I'm doing this is because I recognize that both of these numerators, both of the 2 terms in the numerator now, have x squared minus 1. So that might be useful in the future to think about. Because looking at my denominator, this is actually the product of a difference of squares, right? So here, if I was to multiply x plus 1 times x minus 1, it becomes x squared minus 1. Oh my God. What do you notice? Or what hopefully do you notice? Ah, yes. Every single term here in the numerator has an x squared minus 1, meaning I can cancel x squared minus 1 out of both terms, leaving me with just x plus 1. Whoops, I was about to multiply. There's a minus between those. Minus x minus. And what I'll do from here is I will distribute the negative into my second binomial there, making it become x plus 1 minus x plus 1. The x's, whoa, the x's will cancel, right? X minus x cancels out, and 1 plus 1 is 2. Is that what I was trying to end up with? I have proven this algebraic identity. I have made the left-hand side be the same as the right-hand side. This is an algebraic proof. I believe that you did this in Algebra 1, but I think that in Algebra 1, they made you write down exactly which identities we're using each time, like a multiplication identity, additive identity. We don't have to do that. We don't have to do that here. Okay? We're just doing the math. All we're doing is math. I mean, those words are math. We're not going to write them out. Absolutely don't remember. All right. So now we are going to do this next little example, which is kind of just helping us to organize our thoughts, like the process behind doing these proofs without. So we're going to apply this to something that we can maybe relate to a bit more. We have this little expression here that says, how can you change the word love one letter at a time to form the word math, where each letter changes, or sorry, each letter change still maintains an actual word. So you still have to keep writing words here. Trying to what? Just calm down. The idea of changing one thing at a time and still staying true, equivalent to the, is one of the number one strategies to proving trig identity. So we still need to maintain the values. We still need to maintain the original truth of our original statement. But we're doing it one step at a time to get to our end result of math. We're starting with love and changing a letter at a time to form the word math. So there's many ways you could do this. There are many words, right? There are many, many words in the human language, English language. So hold on, Dario. Delete that. Dario just answered the whole thing. Exactly. You guys are really quick about this. My gosh. You're confused though. So I don't think Maeve is a word. Maeve is yeah, Maeve is not how I would say it. What I would do, I think you got the first one right. Love, we can change the word move. We're changing the letter L to the letter O. It's still a word, move is a word, but we're now one letter closer to math. What letter could I change next? Moat. Moat is a word. Moot? Moat? Is it moot? The point is moot. The point is moot, right? The point, it doesn't matter. That's what moot. So M-O-T-E. We're changing the V to a T. It's still a word. We're still maintaining accuracy here. A tiny piece of a substance. I was totally wrong. Moat. So it is moat. How do you spell moot? M-O-O-T? Moot. Thank you, Morris. Obviously was not an English major. Moat. No, not moat. All right. And what can we now change? Yes, we changed the E to an A, and we have mom. So we're only one letter away now. We're one letter away. Yes, we can change the O to an A, and we have ended up with math. So this is the process that we're actually applying to trig identity, right? We're changing a single property at a time, a single part, so that we can end up with the right-hand side of our equation. Calm down, Dario. Relax, take a breath. This is fine. Yeah. Notice we were never going the opposite direction. We were never writing down math and then changing math to equal love. We were always going in one direction. We're always changing love to equal math. Same exact concept here. Or same exact concept when we're doing trig proof, trig identity proof. What was this word? Mom. We always are going to be working on a single side of the equation, never both sides, because you break down, you lose accuracy. All right. That being said, there are a couple of pointers, a couple of things to hold true as you're thinking about solving these proofs. And I'll read them to you. These may not make sense at the time, but I will read through them so that hopefully as you're solving these, you can think that, oh, she did say this about that. Number one is to know the fundamental identities and look for ways to apply them. Obviously, we're virtual. You can have your notes out in front of you at all times. You don't necessarily have to memorize all of these identities, right? We have them out in front of us. But it is good to be familiar with them. It's good to have kind of an idea of what identities look like. This will save you time. This will just save you time. And obviously, our tests are timed. So saving time is a good thing. Try writing all expressions in terms of sine and cosine. Anytime you're, this is a very, very good strategy to have. Try converting everything into sine and cosine. This helps us become unstuck. Hopefully, help us equal the other side of the equation. When one side contains only one shape function, attempt to rewrite the other more complex side in terms of that function. What this means is if we have an equation, instead of working on the side that seems less complex, instead of working on this side, we would work on the complex side to eventually equal the non-complex side. Whoops, I meant that to be an eraser. This will make more sense. Don't draw on that one, obviously. If, now I hate this because this should not be cross this out. There is no choosing. Work with only one side of an identity. Continuously refer back to the other side to see what you are trying to obtain. Pythagorean identities are going to be your number one identities to use. These are used all the time. They're so useful. Use Pythagorean identities to substitute for expressions equal to 1. And then obviously we can still do all of our mathy things. We can still factor, simplify complex rational expressions, find least common denominators, combine fractions, combining like terms, multiplying both numerator and denominator by an expression to obtain equivalent fractions, or replacing a binomial with a monomial. All of these things can be done to try to make one side of the equation equal to the other. All right, now we get into the actual example because I'm sure you listened to every single word that I just said and understood everything. I don't know about you, but I can't just listen to someone talk. All right, I am going to